right, today we are looking at conditional statements and inductive and deductive reasoning. So one quote that I found that I think is really important in this unit to keep in mind is that the force of logic, the force of any argument we make, comes from the way information is structured. So today is all about structure. First off, we're going to talk about this idea of what is a proof. So a proof is a logical argument using deductive reasoning. Okay, and I'm going to talk about deductive reasoning in just a moment. So first, I'm just going to formalize it as a logical argument using deductive reasoning. So the proofs that we're talking about in geometry, we're looking at these formal arguments that use deductive reasoning. So when we justify our statements, we cite information that we already know as fact. We cite properties, we cite definitions, we cite postulates. And once we've proven a theorem, we can use it in our new proofs. Okay, so I'm going to add that. When we justify a statement, we cite properties, definitions, postulates, and other theorems. Okay, so our formal geometric proofs are using deductive reasoning. Deductive reasoning is concrete, based on things that we know to be true, based on fact. Okay, when we talk about a conditional or a conditional statement, it's really thinking of something in a certain structure. It's an if-then statement. So we're saying if blank, then blank. But I could add to that. So if my hypothesis, then my conclusion. Okay, so if I say something that's just a statement, like girls like bikes, okay, all I'm doing is restructuring that as a conditional. So if there is a girl, then she likes a bike. So again, it doesn't have to be true, right? It's really about the structure. It's an if-then statement. So if the hypothesis, then the conclusion. Okay, logical notation. So here our book uses P to Q, so I'll stick with that, P to Q. P with an arrow to Q. So it's saying that here is our hypothesis, and it should imply or lead to our desired conclusion. And I could actually say P implies Q. The hypothesis implies the conclusion. A counterexample is a specific example that helps us illustrate why a statement is false. Let me write that. So a specific example, let me write that correctly. So a specific example that shows a statement is false. So let me give you an example. Let's say something like all apples are green. Okay, so if I wrote that as a conditional, I could say, well, if it is an apple, then it's green. And that's not true, right? That's a false statement. But if it's a false statement, I have to come up with an example that shows why it's not true. So I'm looking for a type of apple that is not green. So I'm assuming a truthful hypothesis, but a faulty conclusion. So I'm looking for a type of apple that's not green. So an example, a counterexample, could be something like a red or a yellow apple. So again, a truthful hypothesis, but a faulty conclusion. So a type of apple that's not green. So a counterexample could be a red apple, could be a yellow apple. All it takes is one. All right, so in example 1, transform each statement into a conditional. So my statement is that high heels are shoes. Okay, so I'm going to say something like, if there are high heels. I'm going to abbreviate. If there are high heels, then there are shoes. Okay, my filler words don't really matter. So I can say, if I see someone wearing high heels, then that person is wearing shoes. That is fine. That is perfectly fine. Okay, so you can add a few extra little filler words to make it make sense. But I'm looking for something that says if, along with something about the high heels, the then, something about the shoes. Okay, the filler words are fine. Okay, for B, linear pairs are supplementary. Okay, so again, few filler words is fine. So I'm going to say, well, if angles form a linear pair, so I'll start with that. Again, I'm just going to abbreviate linear pair. Then they are supplementary. Right? We know that supplementary means that their measures add up to 180. Okay, so if angles form a linear pair, then they are supplementary. So we're just paying attention to the structure, the if, the then. If hypothesis, then the conclusion. Okay, negation. To negate a statement, you're literally saying the opposite. So it's the opposite of the original statement. All right, so negation, to negate something, means the opposite of the original statement. So we're saying, okay, well, not P, which is the same as using this little symbol with a P, right? It's like the top of what we write when we do a congruent statement, right? We use that little squiggle, so not P. So for example, write the negation of each statement. The car is white. So we're saying, okay, well, what's the opposite? The car is not white. Okay, if I say in B, it is not snowing, right? What would be the opposite? Well, it is snowing. So to negate is to write the opposite of the original. Okay, a few related conditional statements. Here, we're starting with the original conditional. We're going to look at its converse. We're going to look at the inverse, and we're going to look at the contrapositive. So here, I'm going to use P. I want to remind you that that represents the hypothesis. And Q is, of course, the conclusion. So I'm going to write in words and I'm going to write in symbols. Let me just slide that up a little bit. So in words, if I'm writing a conditional, I'm just saying, okay, well, if P, then Q. If my hypothesis, then my conclusion, right? We already talked about this one. It's a P with an arrow to Q. Okay, the converse, all we're doing is we are swapping the hypothesis and the conclusion. So we would say, if Q, then P. So here, the Q has the arrow leading to the P. Okay, the inverse, we're looking at the conditional, and we are negating it. So we're saying, if not P, then not Q. So again, the inverse is taking the original conditional and negating it. So in symbols, we'd say, well, not P to not Q. And then the contrapositive, here, we are negating the converse. So we would say, if not Q, then not P. So not Q to not P. Okay, so all of this is just formal notation. The conditional is the original, the converse. All we're doing is swapping the hypothesis and the conclusion. The inverse is negating the conditional. The contrapositive is negating the converse. So let's do an example together. So let the hypothesis be, you're in New York City. And Q, the conclusion, you're in the United States of America. So write each statement in words and notation and decide whether it's true or false. Okay, if it's false, we know to provide a counter example. So the conditional would be, well, if you're in New York City, then you're in the USA. So if, I'm just going to say if New York City, then USA. So I'm just writing it shorthand, right? So if you're in New York City, then you're in the USA. So is that true? Can you think of any time that you're in New York City and not in the US? Right? No, that's absolutely true. So write absolutely true right off to the side. And my notation would be P to Q. Hypothesis implies conclusion. Okay, my converse, I'm just going to swap it. Right, my converse is saying Q to P. I'm just swapping the hypothesis and the conclusion. So here, if you're in the USA, then you're in New York City. Okay, so we've just come across one that is not true, right? That's absolutely false. Right, what we're looking for here is, can we think of any time that we're in the United States, but we're not in New York City? And I can think of many examples. So I'm just thinking of a counter example. I'm just going to write it as CE for counter example. Okay, so something close to home, a time that we're in the US, but not in New York City. We could be in San Francisco, for example. Right, so that would be an example that illustrates why that statement is not true, why it's false. Okay, the inverse is going to negate the original conditional statement. So we're saying not P to not Q. So if we are not in New York City, then we are not in the USA. Okay, so can we think of any time that we are not in New York City when we are still in the USA? Yes, I can think of places that are not in New York City that are still in the USA, right? So this is a false statement again. And a counter example, right? I'm trying to think of anywhere that's not New York City, but is in the USA. So I'll use a different city. We'll talk about LA this time. Okay, so anywhere that's not New York City, but is part of the US. All right, your contrapositive here we are negating the converse. So we're saying, okay, well, not Q to not P. So if you are not in the USA, then you are not in New York City. Okay, so if I'm not in the USA, is it possible to still be in New York City? Well, no, right? I can't be in New York City either. So this is a true statement. So if it's true, then I don't have to provide a counterexample to show why it's false. I can't come up with a counterexample. Okay, one thing I'm going to formalize when we look at the second sheet is that these will always go hand in hand. So my conditional and contrapositive will always be both true or both false. The converse and the inverse will either be both true or both false. Those will always go hand in hand. Okay, take a moment and grab that second sheet of paper. Just move mine over and slide it down. Okay, so here at the tippy top, right, that's what I just said. So a conditional statement and its contrapositive are either both true or both false. The converse and the inverse of a conditional statement are either both true or both false as well. All right, so a definition, when we call something a definition in geometry, we're saying, well, both the conditional and its converse are true. Because if the original conditional and its converse are true, then the inverse and contrapositive, well, they've got to be true as well. So to be a definition, the conditional and its converse must be true. Okay, for something to be a biconditional, we're really just talking about a structure. We're saying we're going to take that definition and we're going to put it in this structure. So I'm going to write a little note here. We write our definitions in biconditional form. Okay, to write something in biconditional form, we're saying it's true both ways, so the logical notation would be P and Q like this, but a double arrow in between. So P implies Q and Q implies P, right? It's true in both directions. And the way that we write this, we leave a big space right here. We write if and only if, and then a big space right here. So here is our hypothesis. If and only if, the conclusion. Okay, so let's do an example. So example 4, all right angles are 90 degrees. Is this a definition? If so, write the definition in biconditional form. So let's think about it. If I write it as a conditional, if it's a right angle, then it's 90 degrees. Well, that's true. All right angles are 90 degrees, right? I can't think of a right angle that's not. And if I go in reverse, if an angle has a measure of 90 degrees, then it's a right angle, right? That's also true. So it's true as a conditional and its converse, so it is a definition. So we're going to say yes, it is a definition because the conditional and converse are true. Okay, and then if I want to write that definition in biconditional form, we would say the hypothesis, so something about the right angle. So I'll say it is a right angle. We use that filler language of if and only if. It has a measure of 90 degrees. Okay, so for For a statement to be a definition, both the conditional, the converse must be true, and then we can structure it in biconditional form. The hypothesis, if and only if, the conclusion. All right, example 5. Decide whether each statement about the diagram is true. Explain your answer. So, is the measure of angle AEB 90 degrees? Is this 90 degrees right here? Well, I'd have to say yes, because these are perpendicular pathways. So all of these angles are right angles. I could also just view this as a straight angle. So I have a linear pair, and if that's 90, then that has to be 90 too. So I'm going to say absolutely true. I recognize that because BC's pathway, that straight line, is perpendicular to CA, right? Or I could talk about a linear pair as well. Okay, next, points A, C, and D. So A, C, and D are collinear. Well, that's false, right? They're non-collinear. All three of them are not all on the same straight pathway. These points, A, E, and C, those would be collinear. So I'm going to say false, and I'm saying what? They are non-collinear points. Okay, and then AC, so here is A, C, that ray, and CA would be here to the left. Those are opposite rays. Well, that's not true, right? To be opposite rays, they have to have the same end point. So what I could make opposite rays, if I picked where E is, I could say that ray EA and EC, those are opposite rays, but I need to have the same endpoint. So I'm going to say false. We should have the same endpoint. Okay, and my example was I could have EA and EC. So EA and EC are opposite rays. All right, a logical chain. So a logical chain is where we link conditional statements together. Okay, we're just trying to sync them up into proper order. Let me slide my page up. All right, so a logical chain, we are linking conditional statements together in proper order. So let me give you an example. Put the statements below in order to form a proper logical chain. Then write the resulting conditional. So I have three statements. What I'm looking for is which is the hypothesis that starts it off? Which is the hypothesis that there is no mention of in any conclusion? So if I skim through, if there's a parade, then fireworks will go off. If it's July, then flags are flying. If flags are flying, then there's a parade. It's the July one. I see no mention of July over here. So I'm looking for the hypothesis that is not mentioned in any conclusion. So if it is July, then flags are flying. That's the first statement. Okay, and then I pick up here. Here's the mention of flags flying. Here is C. If flags are flying, then there's a parade. Parade syncs up here. If there's a parade, then fireworks will go off. So the order is B, C, A. If it's July, then flags are flying. If flags are flying, then there's a parade. If there's a parade, then fireworks will go off. So my resulting conditional would be, if it is July, then fireworks will go off. So again, it's always right here, the starting hypothesis and the resulting conclusion. So the final conclusion. All right, so if it is July, then fireworks will go off. All right, lastly, we're just talking about reasoning. We have two types. We have inductive and deductive. So inductive is a bottom-up approach, works from specific to general. Arguments are typically based on experience or observation or some sort of pattern that we are recognizing. Deductive is what we're going to be using in our formal geometric proofs. It's more of a top-down approach, works from general to specific. Arguments are typically based on laws, rules, or other accepted principles. So we think of deductive as a little bit more concrete, based on things that we already know to be true. So we're looking through our 4 statements, and we're looking for, is it inductive or deductive? So for A, each time you forget to do your math homework, your parents take away your phone privileges for a day. Well, that feels very specific, right, based on your own personal experience. And then it's followed up with, so the next time you forget to do your math homework, you'll lose your phone privileges. So that feels inductive. Right? We recognize a pattern. It's based on experience. Okay, next one. If you live in Nevada, you're between the ages of 16 and 18, then you must take driver's ed to get your license. So it's a nice broad general statement. Okay, Marcus lives in Nevada, is 16 years old. He has his driver's license. Therefore, Marcus took driver's ed. So this is working from something very general to specific. So this is deductive reasoning. So general to specific. Okay. For the past 3 Wednesdays, the cafeteria has served mac and cheese for lunch. Dana concludes that the cafeteria will serve mac and cheese for lunch this Friday. So again, this is based on something more experiential, observation, right? It's a pattern. This is inductive reasoning. Right, so again, I said it's a pattern and experiential. All right, last one. A number can be written as a repeating decimal if it is rational. So again, a nice broad general rule about repeating decimals being rational numbers. Okay, followed up with pi cannot be written as a repeating decimal. Therefore, pi is not rational. So again, we're looking at something that is general to specific. This has to be deductive reasoning. So deductive. And we're saying because it's general to specific. All right, have a lovely rest of your day.